point. And this point is B, called B0. So you are trying, what are you looking for? You are looking for the equation of the probability density function, which are those two lines, the two lines that define the triangle. So therefore, basically, you are trying to determine the equation of two lines. That's all you are trying to do. How can you determine the equation of a line? If you know the 2 points that are on the line, you can use the 2-point form of the equation of the line and find. So for each line, you know 1 point that's on the line. So all you have to do is find the second point that's on the line. Now, what is the second point? Well, the x-coordinate of the second point is going to be C. How about the y-coordinate? What would that be?
The function of C, right? F of C?
I'm sorry?
F of C?
Well, not quite, but here is whatever this height is, right? That will be that height.
Oh, I'm not.
Close.
That height. So all you have to do is determine the height in terms of ABC. Can you do that? Well, you can't do that because
You can.
Because
the total area under the curve is 1. So 1 is equal to the area of the triangle, which is what? 1/2 times base times height. But base is b minus a, height is h. So I get this equation, 1/2 b minus a times h equals to 1, which gives me h is equal to 2 over b minus a. So this number here is 2 over b minus a.
There's 2.
I'm sorry.
Now, I know these 2 points, and I know these 2 points, so I can write the equation of both lines. How do you write the equation of the line if you know the 2 points on the line? Well, the equation will be y minus y1 is equal to y2 minus y1 over x2 minus x1 times x minus x1. And that should solve the problem. That's it. Now, once you get the equation of these two lines, right? Of course, the first line is, the first equation is valid from what? A to C. The second equation is valid from C to B. Then you, to find the distribution function, the cumulative distribution function, what are you going to do? You're going to integrate those. First one from A to X, second one from C to X. But in each case, you're integrating what? A linear function of x. So in each case, you're integrating something like 5x plus 3. So in each case, your answer would be something x squared plus something times x. And that would be the actual integration problem should be very simple because you're just integrating first power of x.
So would you? So well, I mean, wouldn't you integrate just the x or the entire x minus x?
So of course the entire thing.
So you treat that as a single variable?
No, you do the whole thing. But if you integrate 3x plus 5, your answer will be 3 over 2x squared plus 5x.
That's what I'm saying.
Yeah, that's what you do. So you'll just get a quadratic expression for the distribution function, a linear expression for the density function, and a quadratic expression for the distribution function. Right?
Yeah,
So that should be.
So I mean, I looked up the solution online,
Okay.
and they had a squared term on. So in parentheses, but they squared it.
Well,
But
yeah, I
they
mean,
put it
then
C
you can rearrange terms and do stuff, but that's still a quadratic. They probably have some x minus something squared times a number, etc. But
So
that's
they,
still
so they actually integrated it, had everything solved out. Because
Right.
I was having trouble putting it back together. So then they put it back together, and that's what they
Yeah, you don't have to. You can just leave it as is. All right. And mind you, if you're ever going to do something online, which I know most of you are, I would look at these 2-3 different places because anybody can put anything they want anywhere they want. So just you see one result somewhere does not necessarily make it. Yeah, right. So you always remember there's still a flat Earth society that believes the Earth is
Flat, yeah.
separate.
All over the world, you know?
Yeah. Yeah.
All around the world.
The density function is going to be a linear function, a line.
This is
And
sweet.
when you
It's clever.
integrate that,
Hmm?
the
It's clever.
distribution function is going to be a quadratic.
Oh my god.
All right.
2 times c minus 3 divided by b minus 3 times the difference.
Touch it, but look online. Kind of.
It makes much more sense.
Oh,
So you say it's 2, it'll be 2
okay.
times.
C minus a
Right,
divided
or
by
I can
b side
show you.
Oh, okay.
for, but this is all
Alright.
negative.
What were we doing? So last we had started talking about continuous distributions. We saw all the properties of continuous distributions, that the integral is going to be 1 because the total area under the curve is going to be 1. We get the formula for the mean, the variance. We discussed how to find the distribution function from the density function, which obviously has been long forgotten, but in any case, we talked about all of those, and then we started discussing specific continuous distributions. I talked about the exponential distribution, which was sort of the inverse of the Poisson distribution. I talked about the normal distribution, which is a very important distribution, and you will see this normal distribution over and over and over again in later chapters. And we talked about some other distributions. And finally, I was going to talk about another ultra important distribution called the gamma distribution. But for that purpose, I introduced something called the gamma function. And we discussed properties of the gamma function, and that's where we are. So let's start our discussion with the so-called gamma distribution.
The PDF derives it to be like that. So we care about the difference between that point and then on the second.
Oh, no, so there's like 2 points, 1, 2, 3, 4.
Well, this 4, right? So it's like outside, outside.
Oh.
So that's 0. Okay, so that's 0 or something.
It's different here and
Let
here.
x
Yeah,
be
that's
a random variable with parameters lambda is a positive real number and
Okay, cool.
r
So that's the PDF.
3. Thanks, bro.
with PDF defined as follows. Lambda to the r, x to the r minus 1, e to the minus lambda x over gamma of r, and x a positive. Then we say x has a gamma distribution. And we talked about how to calculate gamma of r in the previous lecture. If r was an integer, right, gamma of r would be what? R minus 1 factorial. And if r was half of an integer, then gamma of 1/2 was root pi, and gamma of 3/2 was something times root pi, etc., etc. But if r were any other value besides the whole numbers or halves of whole numbers, then you couldn't calculate gamma r by any simple means. You have to develop certain approximate integration or whatever. So we won't be dealing with that. And this gamma distribution encompasses lots of other distributions in it. So let me give you that. If R is an integer, is a positive, well, R is always positive, so we can just say if R is an integer, then f of x will be what? Lambda to the r, x to the r minus 1, e to the minus lambda x over r minus 1 factorial. And what is that? Called? This is called an Erlanger distribution.
It's okay. Well,
So if R is a whole number, then the resulting distribution is referred to as an Erlang distribution. Erlang is the last name of a Swedish engineer that worked with these problems. And of course, if R is equal to 1, then what do you get? This will be lambda. This will be 1. This will be e to the minus lambda x over gamma of 1, which is 0 factorial, which is 1. So you just get this. What do you get? You get the exponential. So this is also a generalization of the distribution we refer to as the exponential distribution. So again, which dealt with the Poisson process. So this is a generalization of all of those ideas as well.
So what is the RP? What is written there?
I'm sorry?
RP, well, next to R minus R equals 1.
R equals 1. This?
Yeah.
2. So this is 1.
Is that in X or that's
to be honest, I have a problem.
This is an X.
okay?
From the class.
3. If lambda is equal to 1/2 and R takes on the values 1/2, 1, 3/2, 2, etc., then the resulting distribution is called chi-squared distribution. Which is also a very important distribution. And you use this distribution, chi-squared distribution, you will use this chi-squared distribution when you take the next level of this course, STAT 354, and you talk about regression analysis and you deal with problems involving regression, then you will see this chi-squared distribution in the set. But again, as you see, it's just a special case of this gamma. So that's what makes the gamma distribution a very important distribution. Once you learn about it, you're also learning everything about the Erlang distribution, or the exponential distribution, or the chi-squared distribution, because all of these are just special cases of the gamma distribution. The mean and the mean of a gamma distribution is mu equals to, or E of x equals to R over lambda. And which makes sense because what was the mean of an exponential distribution? 1 over lambda. And remember, the exponential distribution is gamma distribution with r equals to 1. So that's also possible. And what's the variance?
Is this R over lambda
Yes.
or R over X?
R over lambda. Variance would be r over lambda squared. And again, that is in line with what we discussed with the exponential distribution. With the exponential distribution, it was 1 over lambda squared. So now this, in this case, it's r over lambda squared. All right. All right. Suppose close to a telephone system can be described by a gamma distribution with lambda equals to 7 and r equals to lambda equals to, let's say, 0.5 and r equals to 6. Determine probability of x being equal to 4. Find the mean. Find the variance and the standard deviation. So the probability of x being equal to 4, which will be f of 4. So remember, f of x is lambda to the r, x to the r minus 1 e to the minus lambda x over gamma of r. So f of 4 in our case would be lambda, which is 0.5, to the r, which is 6, x, which is 4, to the power r minus 1, which is 5, times e to the minus 0.5 times x, divided by gamma of r. So this would be 0.5 to the power 6, 4 to the power 5, e to the minus 2, divided by 5 factorial. And now you can put these numbers in your calculator and do the calculations and get the answer.
And what is that? The px
That's the probability of having exactly 4 poles coming to the system.
equals f of 4.
Right.
So f of x equals that thing you had before, the Erlang distribution.
The gamma distribution.
And these are all r's at the top,
Right.
each. Are you going to show us more of Minitab today?
No, I'm going to tell you what to do because you all always do the same thing with distributions. You go to probability distribution plot and then choose the name of the distribution you want, then just add the parameters they're asking for. So the only important thing to know from distribution to distribution is what parameters should you enter.
But you get the 5 factorial from?
Because gamma of 6 is equal to 5 factorial. Remember, if r is an integer, gamma of r is r minus 1 factorial.
What does part D say? Find the what?
Find the mean.
Oh, thanks.
So which one are the calculation for
False. Yeah. The mean would be what in this case? R over lambda, and R over lambda in this case is 6 over 0.5, or 12. And the variance, or sigma squared, would be R over lambda squared, which is 6 over 0.5 squared. Something like that. And standard deviation would be the square root of 2.
Why was R over lambda? I know like for the it's kind of like
This was 1 over lambda. In this case, you're generalizing it. Instead of 1, you're looking at R. So, therefore, if you want to establish a parallel, if you're the scientific minds, if you want to establish a parallel between two similar things that happen in the discrete case and two similar things now happening in the continuous case, what would you say? The connection between exponential and gamma function is, you would say, similar to the connection between the blah blah and the blah blah distributions in the discrete case. Both involving R equals to 1 or just in general being R.
Can you repeat that?
Now there are two distributions in this continuous case. There is the exponential and the gamma distribution. And exponential is this gamma distribution R equals to 1. Now we had the same thing with the
Geometry?
right. We had the same thing with the geometric and the
Negative
negative binomial distributions, right? If you take the negative binomial distribution and put one inverse of R, you get the geometric distribution. So in other words, that was measuring the first success. The other one was measuring the R. So what does the exponential distribution measure? This much time between
successes.
two consecutive. Now this is this much time between R. Okay.
that's what I'm
But that's what you're saying. All right. But so this is what I'll say about the gamma distribution. Next, we will talk about the so-called Weibull distribution that was developed by this guy. And it's used a lot in so-called reliability analysis. So, Balodi Weibull is another Swedish engineer. It is similar to the gamma distribution. Oh, before I go there, I'm sorry. Let me add just one more thing to the gamma distribution. This is gamma distribution on Minitel. Now, how did we get the R distributions in Minitab? Be it graphing them, be it calculating probabilities with them, how did we get that? We went to what? Graphs, probability distributions. Then if you want to see probability, we check with probability. If we just want to see the graph, you check single. In either case, once we do check that, we get another box, and in that box, of course, there is a small box where you have the names of all possible distributions, and there you choose the name of your distribution. As soon as you choose the name of the distribution, in the big box, there appears spaces for you to enter your parameters. For example, in the normal distribution, you entered what? You entered mean and standard deviation. For the exponential distribution, it asks for threshold and scale. Threshold, we said, is always going to be 0, and scale was what? Scale was 1 over lambda, or the mean, 1 over lambda, or the mean. Now, if you enter the gamma distribution, it will ask for threshold. It will ask for scale, and it will ask for shape. Threshold is always going to be set at 0. So always put 0 in place of the threshold. Scale would be 1 over lambda. And shape would be r. So once you enter these, then you'll see the graph of this function, and if you want to calculate any probabilities, you can calculate the probabilities using this function. So for example, in my case, in this case, r was 6 and lambda was 2, right? Lambda was 0.5. So for threshold output 0, for scale output 2, and for shape output 6. And if I do that, then I'll get the graph of this function. And then I can also calculate all the probabilities. All right. Now let's go back to Mr. Valodi. So this one, is the Weibull distribution, and let's go one more page here. And this is the equation for the Weibull distribution. Now, let me give you that equation.
Number 8.
As follows.
I think it is.
Suppose
There's no 8.
a random variable
It's a
x
7. That's not
has a probability density function with 2 parameters, beta and delta. And beta is positive and delta is positive. And x greater than 0. So f of x would be beta to the delta, beta over delta, x over delta to the power beta minus 1. E to the power negative x over delta to the power beta.
Does that say beta greater than 0?
Yes.
Okay. Thank you.
Delta is called the scale parameter, and beta is called the shape.
But what is this b divided beta divided by what?
Beta divided by delta.
By delta?
Yes.
X divided. And then beta divided by 1. Can you leave this up?
Okay.
That looks very confusing to write down.
Yeah, it is. It looks like a complicated expression, but in fact, this is much simpler than most others we studied, as you will see soon.
It's a constant.
It does look kind of complicated, but by a simple change of variables, you'll see
Of
that it's
delta?
very easy.
Yeah,
Aren't they all constants though?
All right, and note that
because it's the function of x.
if
It's a number.
Okay.
we put,
And then that's.
oh, I'm
the
sorry,
power of something.
suppose we do blah blah,
And then
then we
times
say
e is the power of something.
x has a rival distribution. Now, this models, it models time until failure of physical systems. So, any physical system you build up will work and work and work and eventually will fail. So let us say you know that the system has a lifetime of this much, let's say 1,000 hours. What's the probability that the system will fail after 700 hours? What's the probability that the system will fail after 1,100 hours, etc. Questions like this are answered by this distribution. So this is the model for time to failure of physical systems. If we put beta equals to 1, then what do we get? This is 1 over, so f of x would be 1 over delta. Now this would be x over delta to the power beta minus 1 would be to the power 0, so this will be 1. So this will be e to the minus x over delta. Now, if you think of 1 over delta as a lambda, this is really like lambda e to the minus lambda x, which is what? Which is the, what distribution is this?
Exponential.
The exponential distribution. So we get the exponential distribution. So again, this is a generalization of the exponential distribution. So what trend are you noticing with these gamma distributions, Erlang distributions, Weibull distributions? Where do these guys starting from? They're mostly starting from the exponential distribution and somehow trying to generalize it in different directions. So that's how they come up with this.
Exponential distribution. What are you trying to write over there?
Yeah.
And this is the exponential distribution. In the exponential distribution, the parameter I used was lambda. So I mean, think of 1 over delta as lambda.
The 1 over delta is x, right?
No, lambda.
Lambda.
Now, x is a variable. Delta is a constant. So delta cannot be equal to x. X represents the variable. The Greek letters are representing constant parameters. All right. Now,
That's what is that? It's lambda e to the negative lambda and then what?
x.
Okay.
X.
All right. Thank you.
The exponential distribution. On which will be tested soon.
So it is 2 tests. After it was one a midterm and a final is two tests.
No, we have a test and two.
Well, now, if you
Next week.
change
Are
the
you
values
free?
of that, you change the shape of the pancake.
Wait,
If you change the
Next week.
values of the scale
No, we have a test
parameter,
next
you
week.
shift the function left and right.
Then
If
that
you change
should
the
be-
value of the shape parameter, you
should be
change the
good.
function shape of the function. So that's what I'm saying. For example, think of the normal distribution. I showed you this earlier. In the normal distribution, you have two parameters. One is the mean, one is the standard deviation. What effect does changing the mean have on the distribution? It shifts. No, it just shifts it left and right, right? It shifts it left and right. So that will be what variable? The scale variable. So that's why usually means are scale variable. Now, what happens if you change the values of the standard deviation? You make the graph wider or narrower, taller or shorter. So you are changing the shape. So that will be the shape variable. Right.
So you're not talking
Well,
about-
always
you're talking
going to be
about-
something because see, if you think about it this way. Now you want you have a distribution function, so the total area under the curve is what? 1. So if I squeeze it somewhere, now area is getting less. So it has to pop up somewhere else to make up for it, so that the total area will be again 1. So that's the change in shape. So that's what's happening. So that's what's happening with the normal distribution. If you make it narrower, now you're losing area, so you make it taller to make up for what you lost, so the total area will remain at 1. So that's the all right. All right. Now, in most of these cases, I did not give you the probability distribution, a formula for the probability distribution case function. For example, the gamma distribution. I did not tell you how to integrate that expression and then get the distribution function and all that, because that would be way too complicated. But in this case, I can do that. I can actually integrate this function and tell you what the
Start rehearsing this one.
distribution function would be for the y distribution.
Good way to like distress, I guess.
But before I do that, let me give you the formulas for the mean and variance. Mean would be delta times gamma of 1 plus 1 over beta. So, this is the gamma function. So that's how we get the mean. So if, for example, beta is 1, this will be what? 1 plus 1, or gamma of 2, which is of course 1 factorial, which is 1. So you can easily calculate. But if beta is 7, then this will be what? Gamma of 1 plus 1 over 7, or gamma of 8 7s, which you cannot calculate. So in that case, you leave your answer in terms of the gamma function. You cannot calculate. So only for very special values of beta can you actually calculate this. What will be those special values?
Integers and halves of integers.
Right, beta could be 1. What if beta is 1/2? Then this will just be 1 plus 2. Or what's beta is 1/3. So if beta is 1 over a number, then you can calculate this. Or
Is this one?
Beta is 2 over a number, you can calculate this. But otherwise, you cannot calculate this mean, and you have to leave it in terms of the gamma function.
So is that 1 plus 1 over beta or gamma?
Yes. Yes.
Over beta, right?
Right, over beta. And the variance would be delta squared times gamma of 1 plus 2 over beta minus mean squared. So once you calculated the mean, then you can calculate the variance as delta squared of gamma of 2 over beta minus mu. So let's do a simple example. Let's say, for example, delta is 5, beta is 1/2. Then what would the mean be? Well, the mean would be delta times gamma of 1 plus 1 over 1/2 or 1 plus 2. So this will be 5 times gamma of 3, which will be 5 times 2 factorial, which will be 10. What would the variance of delta squared 25 times gamma of 1 plus 2 over beta, 2 over 1/2, which will be 4, minus mu squared. So this will be 25 times gamma of 5 minus 10 squared, which will be 25 times 4 factorial minus 10 squared, which will be 25 times 24 minus 100. 2,000, I guess, minus 100 over 9. Check these calculations and make sure they're right. I'm just making this up as I go along.
Yeah, we get plus 4. Oh, that makes sense.
So it does take a little bit work in case of the Weibull distribution to calculate the mean and the variance. And I sort of tailor-made beta, so actually you could do these calculations. Otherwise, you couldn't.
What do you call this formula?
All right. The probability, the cumulative
Tape.
distribution function. Now remember, the cumulative distribution function f of x is the integral from negative infinity to x of the density function. So in this case, f of x would be from negative infinity, but since you're starting from 0, it will be 0 to x of beta over delta x over delta to the power beta minus 1 e to the minus x over delta to the power beta, t. These are t's. Now, t over delta to the power beta, let's let this be u. I'm going to do a change of variables, which of course I can write as t to the power beta over delta to the power beta.
On the last page, I think you made a mistake calculating the
Okay?
25 times 24 minus 1,000. 25 times 24 isn't 2,000.
It's not
No,
600? Okay.
it's 600 minus 100.
Okay, then we'll just upgrade this to 500. All right?
Yeah.
For your f of x, is the integral from 0 to x of 10 Bravo?
Right. Beta over delta, t over delta to the beta minus 1, e to the minus t over delta to the beta. So the exact distribution function. And I'm just going to put u to be this. Then du would be beta delta to the power beta, t to the beta minus, which I can write as beta over delta times t to the beta minus 1 over delta to the beta minus 1. Which is beta over delta, t over delta to the beta minus 1. So this integral this can be written as e to the minus u, and this can be written as just du. It just reduces to the integral e to the minus u. That's what makes this a very simple function to work with, which is minus e to the minus u. So which is going to be minus e to the t over delta to the power beta between 0 and x. At 0, of course, this is 1. So this will be 1 minus e to the minus x over delta to the power.
Is there a negative?
No, because negative makes plus. Minus 3 plus 1. So this will be the actual distribution function, the cumulative distribution function of the function.
Does it say 1 minus e?
Yes, 1 minus e to the power negative x over delta to the power. So, let's work on an example. Because the function starts at 0. Right, so that negative infinity designates the beginning point of this probability density function. So if it's starting at 0, then we start. Suppose the lifetime of a component has a Weibull distribution. With beta equals to 2 and delta equals to 8. So this is problem number so delta equals to 4,000. This is problem number 163 in section 410. What's the probability that x will be greater than 300? So in other words, you know that you have a component that on the average lasts about 4,000 hours and it's modeled by a Weibull distribution. What's the probability that this component will last longer than 3,000 hours? That's where the advantage of knowing the probability cumulative distribution functions comes into play. Remember, probability of x less than a can be calculated as f of a, and probability of x greater than a can be calculated as 1 minus f of a. So therefore, this will be 1 minus f of 3,000. Which is 1 minus, what was my f of x function like? 1 minus e to the minus x over delta to the power beta. So it will be 1 minus e to the negative x, which is 3000, over delta, which is 4000, to the power beta squared. So this would be e to the minus 3 over 4 squared, which is e to the minus 9/16. And you calculate that number, and that would be the result. So, in case of the Weibull distribution, you don't have to integrate to find probabilities because I already did that integration for you and found the cumulative distribution function. So, you can just use that cumulative distribution function. Now, there's another distribution called the log normal distribution, which has some applications, but really not directly related to anything we have done or will be doing in this course. So I'm not going to talk about that. I'm going to skip over that one, and I'm going to talk about the beta distribution. So, but before I do that, let me first introduce something called the beta function. The beta function is a function of two variables, and beta of uv is defined as, this looks like capital B, but actually it is the capital letter beta of the Greek alphabet. It looks exactly like the capital B Latin alphabet, so that's this is really the beta function. Beta. It's gamma of u times gamma of b divided of gamma of u plus. Oops, I'm sorry. Gamma of u plus b divided by gamma of u times gamma of. There are two kinds of beta functions I gave you. So, if u and v are both integers, so this would be u plus v minus 1 factorial over u minus 1 factorial v minus 1. Now let's talk about the beta distribution. You really don't need to know this, but it's an important function that's commonly used in physics and mathematics. So for extra information, you need to write it down. But in this course, you will not be using the beta function. You'll just be using the beta distribution. A random variable x that has PDF or x will be 0 and 1, and parameters alpha beta greater than 0 is called, or is set to beta. Let's go back those to the Weibull distribution. Let me just add this. Weibull on any tab. It will ask for scale, it will ask for shape, it will ask for threshold. What do you guess I'll put in place of threshold? 0. And for scale, I'll put delta, which was called the scale variable. And for shape, I'll put beta, which was called the shape variable.
Wait, what was the scale?
Oh,
Delta.
well, can you show me?
Scale is delta, shape is beta, threshold
I
zero.
call delta the scale variable, and I call beta the shape variable. So logic would be beta, and scale I choose delta, and shape I choose beta. All right. So let's look at some of these, what happens here. If alpha equals to 1 and beta equals to 1, what do I get? The top will be gamma of 2 over gamma of 1 times gamma of 1. And this will be 0, they'll be gone. So it'll just be 1.
So if alpha is 1 and beta is 1.
So what will this become then? Here is 0, here is 1, here this is 1. So what would the beta function become?
Continue, discrete, oh god, it's discrete, it's uniform.
Right. So beta distribution
I'm having a stroke.
then reduces to uniform distribution. What if alpha equals to beta equals to 2?
Oh, but what is that? Is that 1?
Which
No,
one?
on the graph. Is that 1?
Yes.
No, 1 also over there.
And all of them are. If alpha equals to beta equals to 2, what would I get?
His x is probably out because it will look
Gamma
like
of 4, right? Divided by gamma of 2 times gamma of 2 times x times 1 minus x in 0, 1. So this is 3 factorial over 1 factorial, 1 factorial times x times 1 minus x. So it's 6 times x times 1 minus x, which is of course going to look like what? Here is 0, here is 1. It is 0 at 0 and 0 at 1. And it's a parabola that's opening. A parabola that's opening what? It has a negative x squared, negative 6x squared, so it's opening
Outward. Downwards. Sorry.
down, opening down.
No matter math.
So this. So as you can see, the shape of the beta distribution changes a lot. It can be a horizontal line. It can be this line. Now, what if alpha equals to 5 and beta equals to 1? What do I do? So f of x then would be gamma of 6 over gamma of 5 times gamma of 1. X to the 5 minus 1, 1 minus x to the 1 minus 1. So this term will drop. This will come what? 5 factorial over 4 factorial, which is 5. So we'll get 5 times x to the power 4. And you graph this, what do you get? So now this is yet another shape.
I have a question. What is always between 0 and 1?
That's how we define the function, basic function. X is always defined between 0
What's going on?
and 1. X is always defined between 0 and 1. So in other words,
I lost my stuff.
this is going to measure, as we'll talk about, this is going to measure the
Okay, that's all it is.
percent of something that is
Simple, but I gotta
completed,
try it.
probability of completing this percent of a project, right? So the probability of completing this many percent of a project. So you can either complete 0% or you can complete 100%. So it's always between 0 and 1. You can write it for other intervals, but it really won't make sense. I mean, you can do the generalization, but it won't make sense because you want something to be between 0% and 100%. So, if you look at, for instance, alpha equals to 2 and beta equals to 5, then f of x would be what? Gamma of 7, gamma of 2, gamma of
Shab
5.
has like a soccer team, right?
X to the power 2 minus 1, 1 minus x to the power 4.
Yeah.
So this is 6 factorial over 4 factorial, right? 6 factorial over 4 factorial, which is 30 over 30. If you graph this function, you'll get something that looks like this. So I can go on and on and on and on, but what am I trying to show you as far as the shape of this function is concerned? It could be anything. It could be a horizontal line. It could be a parabola. It can look like almost like a normal distribution. It can look like an exponential distribution. So it can look like anything. And so that's what makes this distribution so-called a flexible distribution. By manipulating the values of alpha and beta, I can get any shape I want. All right. So the mean of this distribution is alpha over alpha plus beta, and the variance of this distribution is alpha times beta divided by alpha plus beta squared, alpha plus beta plus.
Oh, okay, sweet, thanks.
this is proportion of the maximum, so beta distribution measures the proportion of the maximum time allowed to complete a project. So let's do an example. The proportion of the maximum allowed time. So that's why your friend was asking why is this between 0 and 1. That's why this is always between 0 and 1. This is, the variable x here is a proportion. So it can be 0 or it can be 1. It's a proportion. It's between 0 and 100%. Between 0 and 1. The proportion of the maximum time allowed to complete a project is a beta distribution with alpha equals to 3 and beta equals to 1. What's the probability? That the proportion of maximum time exceeds So in other words, what am I asking here? Suppose at the beginning of this project, you said we can finish this project in 10 weeks. I'm asking you, what is the probability that the maximum time you work on this will exceed 8 weeks? Yeah? So, this is, of course, is going to be integral from 0.8 to 1 of the f of x dx, which is from 0.8 to 1 of gamma of 3 plus 1 over gamma 3 gamma 1 x to the power
At 2 p.m.?
3 minus 1,
Yeah.
1 minus x to the power 1 minus 1.
2 weeks from now.
So this will be 0.8 to 1.
Registration starts next Tuesday.
Of course, this is 3 factorial. So
Put it
this is
Tuesday,
6
look,
over 2
April 11.
factorial, which is 2, so this is just 3. X squared, this term drops.
What is mine? Oh, no, I'm a junior.
Which is 3 times 1 over 3 x cubed 1.81. So this is x cubed between 0.8 and 1, which will be 1 minus 0.8 cubed. And if you calculate that, that will give you about 0.5. What's this equal to? So there's about 49–50% chance that you will exceed the 8 weeks completed. So you will exceed the 80% of the maximum time we allowed to finish this project. All right.
Pretty much the same, right? You just said it earlier, it was the 8:30.
Okay. So that pretty much covers what I want to cover as far as the homework is concerned, and as far as I believe your test 2 is concerned. Now test 2 is April 5th, Tuesday. Remember, it will be on a Tuesday. It's April 5th, Tuesday. So which Tuesday is that?
That's next week.
Wow.
You should do it next Thursday.
How time flies. So, if you do so, you can
originally it was Tuesday.
Thursday. You're still covering new material.
What's the schedule? 5th and 6th?
Thursday we'll have a review.
Okay, so we're moving ahead to make up for time.
Come up with questions you want to ask.
We're going
me
ahead of the schedule to make up for the snow days.
all those questions. And,
Well, we're way behind homework-wise.
Tuesday,
Yeah.
I said I'll give you
If anything, he's probably just going to condense the homework assignments.
okay.
So, like combine the last 4 into 2 assignments.